Well, hello, and welcome to Doc Onco's Physics. Keith Onco here. What we're going to be working on today is a problem on finding the magnetic force on a wire loop that's partially in a magnetic field. So what you see on the screen in front of you is the convention that we use for a magnetic field that's coming out of the page. If we have a magnetic field that is going to the right, let me switch to pencil mode here, going to the right, we would simply draw an arrow to the right. If it's going to the left, we'd draw an arrow to the left. If it's going up, right, we just draw an up arrow, down. It's easy to draw a down arrow. However, when it's going into and out of the page, it's hard to draw in 3 dimensions. So the convention that we use is if it's coming out of the page, it's a circle with a dot in it. If it's going into the page, it's a circle with an X in it. And the way that you can think about this is if you think of an arrow, if you've ever shot an arrow, if you shoot an arrow and the arrow is moving away from you, what is it that you see? Well, you see the tail end of the arrow. You see the feathers, or they're probably not made of feathers anymore, but that's what you would see. If on the other hand the arrow is coming towards you, you're unfortunate enough to have an arrow coming towards you, what are you going to see? Well, you're going to see, a dot coming at you. You're not going to see the crosshairs, but you're going to see a dot. So that's how you can think of the conventions when we talk about magnetic fields, because we're talking about things in 3 dimensions. So what I have here on the screen in front of you is a magnetic field coming out of the page. And what I'm going to do is I'm going to draw in a wire loop that is partially encased in our magnetic field. Okay? And so parts of our wire loop are in the magnetic field, but parts of it are not. The parts that are in the magnetic field are this section of wire here, this section of wire right here, and the section of wire over here on the left. Okay? The section of wire on the right is not in the magnetic field. So the section that's circled there is not in the magnetic field. We're going to have a current that's going to run, and we're going to say that the current is going to run counterclockwise. So it's going to come in from the right, it's going to go up in that wire, it's going to go to the left in that wire, it's going to go down in that wire, it's going to go to the right in that wire, and then finally up and out. So we're going to have an electric current that's going to be running, and we'll say that that electric current is going to have a value of, we'll make I equal to 3 amps. Okay, and each side of our square loop is going to be 3 centimeters. So the length of our wire in each case is going to be 3 centimeters or 0.03 meters. And the value of the magnetic field, the strength of the magnetic field, is going to be 0.005 Tesla, or 5 times 10 to the minus 3 Tesla. Okay, what we want to know is what the net force is on the wire loop. All right, because we have 3 pieces of wire that are actually in the magnetic field, and all 3 are perpendicular to the magnetic field. They may be going left, right, and down, but they are all perpendicular to the magnetic field because the magnetic field is coming out of the page. So they're all perpendicular. So they could all have an individual force on each segment of wire. Well, first what we want to do is look at the top wire and the bottom wire. So let's take a look at this segment and then this segment of wire, because they're both in the magnetic field. And this is where we have to be really good at using the right-hand rule. And the right-hand rule that we're going to use is the one where we have a current direction, a magnetic field direction, and a force direction. So if I take my hand here and I point my fingers in the direction of the magnetic field, the direction of the current, and my palm points in the direction of the magnetic field, my thumb is going to point in the direction of the force. So in the case that I'm looking at here is the current is going on the left of the page, so my fingers are going to point to the left. The magnetic field is coming out of the page, so it's going to come out towards me, and the force indicated by my thumb is pointing upwards. And so the force on this segment of wire is going to be in the upward direction. If we can do the same thing with the bottom wire, right, it's going to be a little difficult, especially on the screen here, right? My fingers are going to be pointing to the right. I've got to turn my hand like this so that my palm is pointing out of the page, because my palm is the magnetic field. My thumb, and I'm not sure if you can see it or not, is pointing down. And so the force on this wire is going to be pointing down. Since the current is the same in each wire and the segment is the same length, the force on each one of those segments, since it is equal to ILB sine theta, is going to be equal in magnitude but opposite in direction. So what's going to happen to those two forces on the top and bottom wires? They're going to cancel each other out. Okay, so we don't have to worry about those forces. We do have a force, though, another force on the wire on the left-hand side. Okay, it's going to obey the same equation, F equals ILB sine theta. Theta is 90 degrees because the wire is perpendicular to the magnetic field. Okay, and so what's the direction of the force going to be on that wire? Well, let's see. The current is going down. The magnetic field, so my palm is pointing out away from the screen, right? And my thumb is pointing to the left. And so the magnetic field, the magnetic force for the left-hand wire is going to be pointing to the left. So that's the direction of the force. And that would be the direction of the net magnetic force on this loop of wire, because the top and the bottom wires cancel out. So the only force that's really left is the one on the left-hand wire. So if we plug the values into our equation, well, I is 3 amps. Okay, so F equals ILB sine theta. The length, we said, is 3 centimeters or 0.03 meters. B is 0.005 Tesla, right? And like we said, theta is 90 degrees. The sine of theta is therefore 1. Okay, and when we do the math, we plug this into the calculator, what we get is 0.00045 newtons, or 4.5 times 10 to the negative fourth newtons. Okay, so either one of these is just fine. So 0.00045 newtons, or 4.5 times 10 to the negative fourth newtons. I hope that helps, and we'll see you next time.